So yesterday we went over how to build graphs. We also talked about how to use y equals mx plus b. Okay. So what we're going to look at today are the two kinds of graphs that are going to be most important in this unit for you. Okay. Those are going to be position versus time graphs, and that's what we're going to be making tomorrow when we do our lab. Okay. And velocity versus time graphs, which we'll deal with later on in the unit as well. Okay. So there'll be a lab for each graph type, but tomorrow's lab will be on position versus time graphs. Okay, so what we need to learn today is what can I get from those graphs? What can I read directly off of them? How can I look at the shape of the graph and kind of assume or determine what's going on? And how can I calculate certain values from these graphs? These are the skills you're going to be asked to demonstrate to me on quizzes and tests and labs, okay, in this unit, is being able to look at a graph, a position versus time graph, and tell me what the object is doing. Is it moving forwards at a constant velocity? Is it accelerating backwards? Is it stopped? Okay, all of that kind of stuff is stuff you should be able to tell just from a glance at a graph. All right, same thing for your velocity versus time graphs. All right, so we got to understand what information can be read from the kinematics graphs. Okay, we got to look at how the graphs and the equations that you're going to get on your formula sheet here in a few minutes, okay, show the same information in different ways. Like the formula we've been using thus far. Okay, this is really just a slope calculation from a position versus time graph, and I'm going to show you that in a minute. Okay, that's where that formula comes from. And then show that that's where they're derived from. Okay, so on a position versus time graph, okay, what a position versus time graph shows me is, very simply, where the object is at various points in time. All right, it tells me its position at this time or at that time. From that, I can determine whether the object is moving forwards, backwards, constant speed, accelerating, okay, or whether it's stopped or whatever. I can determine all of that just by looking at the graph. Okay, so if I'm looking at this graph right here, okay, where was the object at time 0? At 20 meters. Yeah, it was at position 20 meters. Wherever that 20 is measured from, that's where it was. It was at position 20 meters. Okay, what did it do for the first second? Nothing. Yeah, it stayed in exactly the same place. Its position stayed the same. It was at 20 meters at time 0. It was at 20 meters at time 1 second. So it didn't go anywhere. So when I see a graph, any kind of graph, where the line is flat, it means that nothing is changing. All right? But here, between 1 second and 3 seconds, the position does change. The object goes from a position of 20 meters to a position of 60 meters. Right? It changes its position by 40 meters in 2 seconds. Okay? Now, is it traveling at a constant speed or accelerating during that part? Okay? I heard a few people say accelerate. Okay? We want to say accelerate when we look at this graph because we see something going up, right? And we immediately assume increasing. Increasing means accelerating. Well, in this case, it actually doesn't mean accelerating. In this case, it means the position is changing, right? Acceleration means to change velocity. In this graph, this is just showing something changing its position. Okay? Each second, how far does it go? Between 1 and 2 seconds, it goes 20, right? And between 2 and 3 seconds, it goes another 20. Did it go the same distance every second? Yeah. Then it's traveling at a constant velocity. Okay? It's not accelerating. It went 20 meters each second. Okay? So this is showing something traveling at a constant velocity. Could I calculate what that velocity is? Yeah, because remember, velocity is the change in position, displacement, divided by the change in time. In other words, the final position of the object minus the initial position. So here's the final position. Here's the initial position. Okay? If I subtract those two, I'll get its displacement. Everyone okay with that? Okay? And then I would divide that by the total time. So I would have 60 minus 20 divided by 2 seconds. 40 over 2 is 20 meters per second. All right, everybody okay with that? Okay. What's the object doing here? Right, it stopped. Okay? It stayed at position 60 meters for a second and a half. Okay? At time 3.5 seconds, what does it do? Starts moving backwards, right? Now its position is changing in a negative way. It goes from 60 back to 20. Okay? So it had to be moving at a constant velocity in a negative direction or going backwards. All right. What's the total displacement of this object over that whole trip? Nothing. The total displacement of this object is 0. It started at 20 meters and ended in the same place. Just like that trip to Walmart we talked about on the first day. Okay? If I go all the way to Walmart and all the way back, my starting and ending positions are the same place. I have not displaced myself from where I started because I ended up back there. Okay? All right. So that said, though, if my displacement is 0, what's the distance traveled for this object? How far did they go here? Okay, so it goes 0 here. How far does it go between here and here? 40 meters. How far does it go here? Doesn't go anywhere. How far does it go here? 40 meters. All right, so the total distance is 80 meters, but the total displacement is 0 because it ended up back where it started. Okay, everyone follow how we calculated those things? All right, does that mean I could also calculate the average speed for the whole trip? Yeah, okay, in the same way that we did just a few minutes ago on the quiz. All right, average speed is total distance over total time. We just calculated the total distance to be 80 meters, and it took 6 seconds. Okay, V equals D over T. What's the average velocity here? Okay, remember, average velocity is total displacement divided by total time. What was our displacement? All right, so what's our velocity then? Also 0. Okay, these are exactly the kinds of questions I would ask you to do on a unit exam. In fact, that graph was on last year's unit exam. Okay. So nothing terribly difficult there, as long as we understand, can look at this graph and know what's going on. Okay? The most important skill is not to memorize what I can get from each graph and how, because that'll only work maybe through Science 10. You get to Physics 20 and we're dealing with like a dozen different graphs. You might be able to memorize that many. Okay? But you get to Physics 30 or Chem 30, and either one of those courses you're looking at easily 20 to 30 graphs that you might deal with. There's no way you're memorizing everything. So it's better to learn how to look at a graph and interpret what's going on, which is what we did right at the very beginning when I said, what is the object doing right here? And you looked at it and said, okay, so position is here and position didn't change. If you don't change position, then you're not moving. Okay, you interpreted what was on the graph. That's an important skill, to be able to look at a graph and interpret what it's saying. Right? There's a lot of people walking around in the world, and if I showed them a graph, doesn't matter what it was, they wouldn't be able to tell me what it was saying. Okay? And that's just basic graphing skills. We got to be able to look at a graph and understand. Okay? Like if I showed you a graph that looked like this, what does that tell you? It's telling you that stock prices are going down. Should you invest in this company? No. Okay? How important is it to have basic graphing skills? You don't have great basic graphing skills, somebody's going to sell you their shares. Okay? They're going to get out of them and you're going to be stuck with them and they're going to be worth nothing. Okay? Being able to interpret a graph is an important skill. Okay, this graph over here on the right, okay, is also a position versus time graph, but it's got a curve on it. Okay, now with a curve, okay, what is this object doing? Okay, let's just kind of break it down. In the first second, did it go very far? No. But what about between 1 and 2 seconds? Did it go further? Yeah, each second, it's going further than the second before. And the only way to go further in the same time interval is to go faster. So this object it's speeding up. This is an accelerating object on a position versus time graph. Okay? As I accelerate, I go further in each time interval. Okay? And so I end up getting a curve, okay, showing me the object's accelerating. Okay, so those are important things to be able to, again, look at a graph and analyze the graph and tell me what's going on. Okay, rather than memorize that, oh, a curve on a position time graph is an acceleration. Okay, I mean, that might get you through Science 10, but it's not going to get you very far after that. Okay, got to be able to interpret a graph. All right, yesterday, we talked about this formula here. Right, and we said that essentially this is a manipulation of that. Okay, that slope is rise over run. On this graph, position is on the y-axis, so this would be y2 minus y1, which is the rise, okay, over t2 minus t1, okay, or that would be x2, sorry, x2 minus x1, which happens to be time on this graph, okay, which is the run. Okay, does that look familiar to people? Okay. All right, and we said this formula can tell us the same thing if we manipulate for m, because m is slope, right? So if I manipulate this formula for m, I'm going to subtract b and divide by x. So I'm still getting the change in y divided by the change in x, okay? Everybody with me there? Right? On this graph, that's what it's showing. I'm just going to extend it back here a little bit. Okay, so what I've got here is that this is b, okay? This would be y, and this whole distance here, sorry, this whole time here would be x. Okay, I'm still doing rise over run, right? Still y2 minus y1. Okay, here's y2, here's y1. Okay, I'm still doing the same calculation. Now, on a position versus time graph, what does m represent? What am I calculating when I calculate the slope of a position versus time graph? Velocity. Okay, how'd you figure that out, Luke? You saw it there? Okay, so yeah, you're good. No, we've been talking about rise over run in terms of velocity. Okay, but look at what we're calculating. Okay, position is on the y-axis. If I go y minus b, have I just calculated the change in position? Right? This is the same as saying final position minus initial position divided by time. Well, that's displacement divided by time. Okay? So v equals d over t is actually just calculating the slope of a line on a position time graph. That's where that formula comes from. We derive it from the graph. Okay? Everybody with me there? Again, that's something that you'll be asked to do tomorrow on your lab. Okay? I'm going to ask you to calculate the velocities of all of the carts that we run down the hallway. Right? We're going to build position versus time graphs of their data, okay? And their data is going to look something like this. Right? So we'll have like probably one car that'll go, whoa, that's not what I want. Okay, something like this, okay? And then we might have another car that's slower. So its points would look like that, right? And Google Sheets will draw best fit lines for us. It'll say, okay, that was car 1 and this is car 2. Which one's faster? Car 1's faster. Its line is steeper. Its slope would be greater. Okay, it's the faster of the two vehicles. That's the kind of stuff we're going to be doing tomorrow. Now, if I calculate the slope of these lines, that would be the velocity of the cars because it would be their displacement divided by their time. Okay. All right, so calculations are important, but like I said, more important is being able to look at a graph and interpret what the graph is telling us. All right, so I have a position versus time graph here. What's the object doing in part A? Moving at a constant speed or a constant velocity in a positive or negative direction? Positive direction. Okay, what's going on in part B? Nothing. Standing still. Its position isn't changing. What's going on in part C? It is what? Well, it's not decreasing its velocity. It's changing its position in a negative direction. Okay, it's actually traveling at a constant velocity backwards in that part. Okay, what's going on in part D? Nothing. Okay, standing still. Where is the object going faster? E or F? Okay, why do we say E? Steeper, right? Okay, it obviously covers greater distance in a smaller time interval, whereas this one doesn't go as far and takes much longer, okay, in order to do that. Okay, next question. I want you guys to see if you can calculate this for me. I want you to calculate the total displacement of this object over the entire 17-second trip. Okay, good. It's 0. How do we know that? Starts at 0 and ends at 0. It starts and ends at the same position. Okay. What's its velocity over the whole trip? 0. Right. Okay, if its displacement is 0 and v equals d over t, v has to be 0 too. Okay, little trick here. What is the total distance traveled? That's going to take a little calculating, actually. Just adding, but it'll take a little bit of adding. Nope, distance can't be negative. Okay, is this just like a v equals d over t question with many parts? It is. Okay, so how far does it go in part A? Well, it goes from 0 to 6, so how far did it go? 6. How far did it go in part B? Didn't go anywhere. Okay, in part C, it goes from 6 to negative 10. How far is that? 16. All right, part D, didn't go anywhere. All right, and then between E and F, it goes another 10 meters, right? All right, so we got 6 plus 16, okay, is 22, plus 10 more is 32 meters. All right, total distance traveled is 32 meters. What's the average speed? Okay, did I already calculate D? Right, the total distance traveled is 32 meters. How long did that take? We said it ended here at 17 seconds. 32 over 17, that would give us our speed, 1.9 meters per second. Okay, these are exactly the kind of things I'm going to ask you to do. Okay, mathematically, have any of those been really hard? I asked you to add some numbers together. I asked you to divide two numbers. Okay? I'm not asking you to do anything mathematically difficult here. Okay? But we do have to be able to analyze a graph. Okay? A couple of years ago on the final exam, I put a graph like this, and all I asked in the question was describe what is going on in like part A, part B, or whatever. Okay? All people had to do was write down what was happening. You wouldn't believe how awful that question went. Okay, like people just didn't get it. Okay, they didn't get that, oh, it's a position versus time graph. So in A, the position is changing constantly, constant velocity. Mrs. Ostafchik, what can I do for you? Okay. Awesome. Okay, so just being able to analyze what was going on. I got a lot of answers like it's accelerating because people just had that like kind of knee-jerk reaction to seeing a line that was going up. Okay, it wasn't speed that was increasing. This graph isn't showing speed, it's showing position. This is showing an increase in position. Okay? I would have even accepted that as an answer. The position is changing in a positive way. That would have also been what was going on in part A. Okay, you guys kind of follow what I'm looking for there? All right. Sometimes you get graphs that have got these curves all over them, okay? And we've got to be able to kind of interpret what's going on, okay? Or I might ask a question that really makes you think and say, what kind of motion is going on in this graph in total? Okay, so what's going on in the first part of this graph? So let's say from about here, actually it'd kind of be all the way to here actually, from here to there. What's that object doing during that part? It's accelerating, right? Okay, it's going further each second than it did the second before, right? But between here and here, what is the object doing? Well, not nothing, because it's not flat. Okay, reaching its peak, that's actually very close. Okay. Exactly. It's losing its energy, it stops for a second, and then falls back down. That's exactly, this graph is this. Here's the part where I'm accelerating the marker. Here's the part where it's flying through the air, slowing down, coming to a stop, falling back to me, and here's the part where I catch it. Okay, that's what this graph is, of me throwing something in the air. Okay, I didn't catch it at the same height, I caught it higher, so I threw it from down here, but I caught it up here, right? So I caught it higher than I threw it from. Right? But what this is showing right here is I'm no longer accelerating the object. Now it's slowing down. It's still a curve, but the curve, instead of getting steeper, is getting flatter. Okay? In fact, if I was to draw a tangent to that curve, it would be flat, okay? Right there at the top. Then it actually curves and starts speeding up in a negative direction. And then here, okay, I see that the curve is starting to get flat again, okay, which means that, hey, I've caught it and I'm slowing it down. And I'm stopping it, I'm catching it. Okay, everybody kind of follow that? Okay. So what this diagram is showing is how do you calculate how fast the object is going when its speed is changing? Okay, it's not something you're actually expected to do anymore, okay, but these triangles allow us to essentially make parts of the graph longer or long enough to do a v equals d over t problem for. Okay, so that's what this is showing here, is drawing tangent lines. That's lines that just touch a curve but don't cross it. Okay, when they touch a curve but don't cross it, they're parallel to the curve where they touch. Okay, and if I can make that line long enough, I can calculate its slope. Okay? It's not something you guys would be expected to do. Okay, but I might give you a graph like this and ask you what's going on. Okay, something like that. Or what's the velocity at part B, because that would be one you would know it's zero here, right? Because it's flat at that instant. Okay. Questions on position versus time graphs. We're going to spend way more time than this on them, but that's just kind of the introduction to them. Okay, so for a position versus time graph, I can read directly off the graph. You might want to write this down. I can read directly off the graph position and time, because that's what's on there. Okay, that's not a trick. Okay, it's that way for any graph. So on a position versus time graph, I can tell where the object is at various points in time. I can also calculate the average velocity of the object, the average speed of the object, the total distance, and the total displacement. Okay? There are 4 things I can calculate with that graph. Average velocity, average speed, total distance, total displacement. All right, and we went over all of those on 2 different graphs. Okay, now a velocity versus time graph shows how fast the object is going at various points in time. Well, how fast and in what direction, because velocity is a vector quantity. Okay? So it shows how fast and in what direction the object is going. Okay. What is the position versus time graph here on the left showing? Moving forwards at a constant speed or in a positive direction at a constant velocity. Okay? The amount of distance is changing every second, right? If it was a curve, then it would be accelerating. Okay, right here is the velocity versus time graph. What is it showing? Something traveling at a constant speed. Okay? How many of you were going something that was stopped? How many of you are thinking that? Okay? Because we just learned, oh, well, if it's flat, it's not going anywhere. That's true on a position versus time graph. On this graph, what's not changing is velocity. Okay? So even though it's flat, it's actually moving. It's just not changing its velocity. Okay? Everyone follow there? Okay? So you have to interpret each graph differently. Okay? In fact, these two graphs are showing the exact same thing, like the same object. They are a graph of the same experiment, but they look very different. Right? This is an object traveling at a constant velocity, and this is an object traveling at a constant velocity. Could I calculate what the average velocity of this object is? I could, right? It would be a slope calculation of this line, right? So that's what I'm going to do. I'm going to calculate the slope of the line in this graph. Okay, I'm going to use this point here for y. This point here is b because that's where the y-intercept is, right, at 100. And the time is going to be 5 seconds. So this is going to be 1400 minus 100 divided by 5 seconds. So 1300 over 5 should be 260, I think. 260 meters per second. Is that about where the line on the velocity time graph is? Right? This is 250 right here. That's just a little bit above it. Okay? Looks to me like they're showing the same thing. Okay. All right. Could I calculate how far this object goes from the velocity versus time graph? Okay, how would I do it? So I know its velocity, right? Its velocity is 260. Do I know how long it does that for? 5 seconds. Could I use this formula? Right? It's traveling at a constant velocity, so I can use this formula. D will equal V times T, which is essentially the area of that rectangle, right? It's base times height. The base is 5 seconds, the height's 260, okay? And I would be calculating that. And lo and behold, it's 1,300 meters, which is exactly what we said it was when we used this graph to do it. Okay, so the two graphs are, again, showing exactly the same information, just from different points of view. All right. Let's say that instead of being a flat line, the graph looks like that instead. What's that object doing? Luke? It's accelerating. Okay? It's accelerating positively because it's speeding up. Okay? Its velocity is increasing from 100 to 550. Okay, but those lines aren't on there, but that's what it is, 550 meters per second, which is, well, really fast. Okay? Like faster than the speed of sound, really fast. Okay? All right, so it's accelerating because we see a change in the velocity here. Now, we haven't talked about acceleration yet, but okay, acceleration is very much like velocity in terms of calculating. Okay? To calculate velocity, I take the final position, subtract the initial position, and divide by time. It's the change in position divided by the change in time. Well, acceleration is the change in velocity divided by the change in time. Formulas look a lot alike. Okay? They're both the change in something over time. So I calculated this using the slope of this line. Could I do the same thing here and calculate this? Yeah. Okay, it's the change in velocity over time. Okay, my change in velocity would be 550 minus 100, that's 450, okay, divided by 7.5 seconds. Okay, that's how long the experiment runs for. Okay, I would then calculate the acceleration, or the rate at which the velocity changes. Okay. All right. Could I calculate how far that object goes? Like, it's not traveling at a constant velocity anymore, is it? Right? Its velocity is changing. But we learned a little bit earlier that average velocity is total displacement divided by total time. Okay. Could I figure out what the average velocity of the object is here? Where would that happen? Where would the average velocity occur on here? Increasing from 100 to 550, where would the average be? Okay. If I tell you what the class average is, that generally means that half of you did worse than that and half of you did better than that. Agreed? Generally, not always, but generally. Okay, so wouldn't the halfway point be where my average velocity is? Half the time I'm going slower than that number and half the time I'm going faster than that number. Okay, so here's what I want you to remember. Just a minute ago, we calculated the displacement of this object by calculating the area of the rectangle. How do you calculate the area of a triangle? Base times height divided by 2. Okay, so wouldn't my average speed be the height of this triangle divided by 2? Didn't we say it was halfway up? Okay, so if I take base times height divided by 2, I'm taking time on the base and multiplying by average velocity, okay, which is exactly what I would do to calculate displacement any other way. Okay, just looks different on a graph, but we're not doing anything different mathematically. Okay, we're still doing the stuff we did before. Now, probably you're looking at this and going, okay, my brain is about to explode, okay, and not in a good way. It's okay, we're going to spend lots of time on graphing. Graphing is a really, really important skill. Okay, so this isn't the only day I'm going to show this to you and then just say, okay, now answer the questions on the test. Okay, we're going to spend lots of time on this. Okay, but if there was one thing that you should go back over in preparation for your unit exam, it would be this lesson between 0 and 34 minutes, because that is exactly the stuff that I'm going to put on there about graphs. Okay, being able to calculate displacement from a velocity time graph, acceleration from a velocity time graph, velocity from a position time graph. Okay, those are the things to be asked to do. All right. Okay, looking at this graph. So this is a velocity versus time graph. What is this object doing? What is it doing here? Yeah, gaining velocity. So it's accelerating positively, right? Its velocity is becoming greater and greater. What's it doing during this part? Not nothing. It's not accelerating anymore. Staying at a constant speed of like about 8 meters per second, according to the graph. And then what's happening here? Yeah, decelerating and actually coming to a stop, right? The velocity actually becomes 0 at this point, which means the object actually does stop. Okay, so it accelerates, goes for a constant velocity, and then stops. This is a graph of someone running a race. Okay, they accelerate, they reach their top speed, they run at their top speed till they get to the finish line, and then they stop. Okay, that's what that graph would look like. Okay, so let me go over this. I'm just going to delete this whole thing and draw it over again, because it'll make more sense if I do it one piece at a time. All right, so let's say that I have a velocity versus time graph. All right, so I got velocity in meters per second on the y-axis, time in seconds on the x-axis. And let's say that my points went something like this. Okay, I draw a best fit line for those points. Okay, looks something like that. All right, this object is clearly doing what? No, it's a velocity versus time graph. It's accelerating, right? Its velocity is increasing. Okay, if I want to calculate acceleration, acceleration is the change in velocity, and this is the formula that you're going to use, okay? Change in velocity divided by time. So VF minus VI over T, right? Now, let's just say that when I graph this on Google Sheets, it spits out this equation. Okay, and it says that y equals 1.7, okay, x plus 2.0. Right? So essentially it's telling me the value right here is 2.0. Okay, this is B. This is the y-intercept. It's where the line crosses the x or the y-axis. It also happens to be how fast the object is going at time 0, which would be then its initial velocity. Okay, let's say that we also happen to have this point right here that's right on the line. Okay, and it's up there. Right, that would be my y value. It would also happen to be my final velocity, okay? The fastest point reached by the object. All right, and then this number here is the slope, yes? Okay, so let's say I manipulate for this number, right? I'm going to take y, and I'm going to subtract 2.0 over to this side, okay? So really, what I'm doing is going y minus b over x equals m, which on this one would be y minus 2.0 divided by x equals 1.7. Essentially, I'm calculating the acceleration by calculating the slope, because what I've done is take VF, subtract VI, and divide by the time. The x-axis is time, so x represents the total time. Y minus b represents final minus initial velocities. Okay, so that formula is also just a slope calculation for a velocity versus time graph. Okay, it's a lot to take in one day, okay, but that's why we're going to spend lots of time practicing it. Okay. Okay, anybody need that diagram anymore? Okay, we already talked about that. Okay, I want you guys to give this question a try. Okay, you have this position versus time graph. I want you to calculate the total displacement, the total distance traveled, average velocity, and average speed. The answers are there in bold, okay, so you'll know if you did it right. Okay, but I want you guys to try and calculate those 4 things, and then we'll kind of walk through it together. All right, let's have a look at this one. So we want to calculate the total displacement. Okay, we have to remember that total displacement is our final position minus our initial position. Okay, our initial position is 0.2 meters, and our final position is 0.5 meters. All right, so all we do is go 0.5 minus 0.2, and our total displacement is positive 0.3 meters. Okay, because we went forwards, okay, or we went in a positive direction on this graph. Everybody okay with that? Okay, if I want to calculate my total distance traveled, then I got to do that section by section. Didn't go anywhere here. Right, from here I went from 0.2 to 1. So that's 0.8. Didn't go anywhere here, and then went from 1 to 0.5. Right, so 0.8 plus 0.5, 1.3 meters. Okay, no sign on that one, no direction, because that's a scalar quantity. Okay, if I want to find the average velocity, okay, average velocity is displacement divided by time. I already calculated the displacement. It's positive 0.3. Okay, divide that by the total time, which looks to be 7 seconds. Okay, and that'll give us our 0.04 meters per second. And it's positive, okay, because it's a vector quantity. And then lastly, the average speed is distance divided by time. I just calculated distance here. Okay, so 1.3 meters divided by 7 seconds gives us 0.19 meters per second. No sign on that one because speed is a scalar quantity. All right. Okay. Prime example of the kind of thing you'd be asked to do on a unit exam or quiz. Okay. Here's a graph. Do the following things. Okay. I could also very easily have asked, what is the object doing between 2.5 and 4.5 seconds? Or sorry, 3 and 5 seconds. What's it doing between 3 and 5 seconds? Well, here's time 3 seconds. Here's time 5 seconds. What's it doing? Nothing. Okay. Standing still. I wouldn't write nothing on a test. Standing still or position not changing would be more technical sounding answers, okay, on a test. Okay, same deal, different graph. Give that one a try.